So for today, we'll be talking about section 2.2 of our course, so titled Polynomials and their operations. So let us start with the following definition. We define monomial. A monomial in the variable x is an algebraic expression of the form ax to the k. Okay, so this is in the variable x. And a here is some real number, and we will call it coefficient. And k here is some power. So we describe this. So where a is constant, called the numerical coefficient of the monomial, and k is a non-negative integer. So take note of that. K is equal to 0 or 1 or 2 or etc. So non-negative integer. Okay. If a is not equal to 0, meaning the numerical coefficient here is not equal to 0, we will call k to be the degree of the monomial. Okay, degree of the monomial. In other words, a monomial in one variable is the product of a constant and a variable raised to a non-negative integer. Okay, and this variable here, this whole thing here, okay, sometimes it is called this guy here, the x to the k. Sometimes it is called the literal coefficient, but it's not commonly used nowadays. So we will not be talking about, or we will not be stating this literal coefficient. And therefore, since we are only going to consider numerical coefficient, okay, the constant part attached to the variable. So a x to the k. So a is the numerical coefficient. We'll just call it coefficient. Okay. Okay. So here are some examples of monomials. So here we have 3x to the 4. So 3 here, it's the coefficient. And 4, you see here, the exponent of x. So this is the degree of the monomial, 3x to the 4. Another example here, it's negative 4x. Okay, so negative 4, that is the coefficient. And in here, you don't see a number. Exponent of x, you don't see a number. But the exponent, when you only see the variable, okay, without a superscript, the exponent is actually 1. Okay, so remember, any number raised to 1 is the number itself. Okay, so x to the 1 is simply x. And therefore, this monomial, negative 4x, has degree equal to 1. Okay, next example here, you have square root of 3x squared. So the number here, square root of 3, is the coefficient of the monomial. And the power 2 here, it's the degree of the monomial. Next here, if we only see the constant 5, okay, take note that 5 can be written as 5x to the 0. Okay, remember, for any non-zero number, if you raise it to power 0, then that number becomes 1. So remember this from the last lecture. So a to the 0, this is equal to 1, provided that a is not equal to 0. Okay? So here, if we have a variable, we will always assume that if we have x to the 0, we will always assume that that variable x will not take 0. Okay? So this here, the constant 5, which can be written as 5x to the 0. Okay? So we have the monomial. The coefficient is 5 and the degree of the monomial or the degree of the constants is equal to 0. Okay? And then we have here negative 8x squared. Coefficient is negative 8 and the degree of the monomial is equal to 2. Okay? Any questions so far? Now, let us look at some examples which are not monomial, and we will see or explain why they are not monomials in our definition or based in our definition. So in here, we have 3x raised to 1/3. So this is not a monomial because the exponent of the variable x is 1/3. Remember that according to our definition, the exponent of the variable for a monomial is a non-negative integer. So exponent is not an integer in this case. So this is not a monomial. And then we have here 5x raised to negative 2. This is also not a monomial since the exponent of the variable x is equal to negative 2. And we define monomials to have the variable to have non-negative integer, and negative 2 is a negative number. So we will not call this a monomial based in our definition. Okay? And later on, we will see more examples which are not monomials, or even we extend our definition to other to polynomials. Okay, so two monomials with the same variable raised to the same power are called like terms. So for instance, we have this 3x cubed and negative 2x cubed. So the variables are x and x, and the exponent for those variables are both 3 and 3 in here. So we call these two monomials like terms. However, if we have this 2x cubed and then the other one is 2x squared. So these two guys here are not like terms because even if they have the same variable, they don't have the same exponents. Okay? So like terms, same variable raised to the same power. Okay? So in this example, you have the same variable, but the powers are different. Another example here, you have 5x cubed and 3y cubed. So again, these two are not like terms because we see here different variables. One is with variable x, the other is with variable y. So even if they have the same exponent, they are both 3, okay? They don't have the same variables. So they are not like terms. Okay? So what is it to us if we consider like terms? Okay? So if we have like terms, we can add or subtract them. And we will use distributive property of real numbers. Okay, so we will use the distributive property of one number over the sum of two numbers, or the reverse of that. Okay, so in order to see that, we have the following. So for example, you have 2x to the 4 plus 5x to the 4. Okay, 2x to the 4 and then 5. We want to add it from 5x to the 4. So notice that these two are like terms, 2x to the 4 and 5x to the 4. They are like terms. They have the same variable and the same exponent. Okay, but you have 2 here and you have 5 here, and this one can be written as 2 plus 5 and then x to the 4. Okay, so from this side going to that side, we actually did some distribution. Okay, but from this left hand side going to this right hand side, what we actually did here is called factoring, and we will discuss factoring in more details next meeting. Okay, but for now, if we have like terms, we can add or subtract them using that distributive property, or in the reverse, the factoring. But anyway, so you have here 2 plus 5, and therefore we will get 7x to the 4. Okay, next example here, you have 3x cubed plus negative 2x cubed. So again, like terms, you can add them. Okay, we have 3 here and we have negative 2 here. So this one is 3 plus the negative 2x cubed, and therefore we will have, so 3 minus 2, that's 1, and 1 times any number is the number. So you have x cubed here. Okay, there is a 1 here multiplied to x cubed, but again, 1 times any number is the number. So we don't have to write 1 in this part here. Another example here, you have 2x minus 5x. So we will have 2 minus 5x, and we have here negative 3x. Okay? Now, we were able to add or subtract like terms. So what about those terms which are not like terms? Can we actually add them? Well, we can add them. Okay, we can add them, but you will not be able, or we will not be able to simplify them. Okay, so if we add or subtract two monomials which are unlike terms, okay, then what we will get is called a binomial. Okay, so from the word mono, single, this time here we will have binomial. So from this prefix bi, meaning two. Okay, so the sum or difference of three monomials with three different degrees, okay, we call it a trinomial. Okay, so three different degrees. So definitely they are all not like terms to each other. Okay, but we have three monomials. We will call the sum or difference trinomial. So again, the prefix tri here tells us we have three monomials in the sum or difference. Okay, so for example, here we have x squared, and then here we have the constant 1. Okay, and then we add them. We cannot simplify this anymore. Okay, so if we add them, we'll just have x squared plus 1. So this one is called a binomial. Okay, another example, here you have 2x squared minus 5x squared plus 3x. So you are adding three monomials in here. But notice, 2x squared and minus 5x squared, they are like terms. So you can simplify them using the previous slide. You can simplify them, and this expression here can be written as 2 minus 5x squared plus 3x. And notice, this simplifies to minus 3x squared plus 3x. And after simplifying this expression on the left hand side, we only get two monomials being added, minus 3x squared and then the 3x. Okay, so this expression on the left hand side is actually a binomial, even if it started from three monomials being added. Okay? And then here we have x cubed plus x minus 1. So we have three monomials here, and they have different degrees. This is of degree 3, this is of degree 1, and then this is of degree 0. So three different degrees. So we have here a trinomial. Okay? Questions so far?
No, it's okay.
Okay, good. So, can we actually have a sum of four monomials or sum of five monomials with different degrees? So, the answer is yes. But for those cases, even these cases here, the binomial, trinomial, and even the monomials, okay, they can land in the following category. So, if you have sum of monomials, okay, sum of monomials, then those can be called a polynomial. Okay, so a polynomial in the variable x is an algebraic expression of the form, this form here, a sub n x to the n plus a sub n minus 1 x to the n minus 1 blah 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 until plus a sub 1 x plus a sub 0. Okay, so notice the labeling of the coefficients, okay, for each of the monomial. So x to the n, the power of x is n. We use subscript n for the a. Okay, the power n minus 1 for this variable x, we use the subscript n minus 1 for the coefficient a, etc. So it's easy to remember this kind of labeling. Okay, now this a sub n, a sub n minus 1, a sub 1, a sub 0, these are constants, okay, and we call them coefficients of the polynomial. Okay, we call them coefficients of the polynomial. And here n is a non-negative integer. Okay, non-negative integer, so it can be 0, it could be 1, 2, 3, etc. Okay, now if this guy here, a sub n, is not equal to 0, okay, we call it the leading coefficient. So it is the coefficient of the variable with the highest degree. Okay, so in this case, the highest degree is n. Okay, and then here we call the coefficient of that variable with the highest degree or power the leading coefficient. And I already mentioned leading here, we will have the leading term. So the part here, okay, a sub n x to the n, we will call it the leading term. Okay, and n here, okay, that non-negative integer n is called the degree of the polynomial. Okay, called the degree of the polynomial. So again, take note if you have a sub n not equal to 0. Just like in the definition of the monomial, if the coefficient is not equal to 0, then the degree or the power of the variable there is called the degree of the monomial. So for the polynomial, we will look at the highest degree in the expression. Okay, and that becomes your degree of the polynomial. So in short, a polynomial is just a sum of monomials. So this is a monomial here, this is another monomial here, some more monomials in here, and then monomial here, and then monomial here. You just add them. Okay, if you need to simplify them, meaning if the monomials, there are monomials which are like terms, you can add them and simplify them. Okay, until all the monomials in the sum have different degrees already. And you will have that simplified polynomial. Okay? Sum of monomials. So let us look at the polynomial again. So a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1x plus a sub 0. So each monomial is called a term of the polynomial. So this here, we called this earlier the leading term. Okay? But all of them, this guy here, this guy here, this guy here, and this guy here, we call them terms of the polynomial. Next, if all the coefficients of the polynomial are 0, okay, the polynomial is called the zero polynomial. And in that case, okay, we say that the polynomial has no degree. Okay, the zero polynomial has no degree. And I will explain why we just say that the polynomial has no degree later on. Okay, now polynomials are usually written in standard form, beginning with the leading term, the non-zero term with the highest degree. So beginning with this term, okay, and continuing with terms in descending order according to the degrees. Okay, so next to the leading term is the term with the next highest degree, okay, etc., etc. Okay, so decreasing order of degrees for the monomials. So if you find some polynomials which are not written in standard form, try to write it in standard form. And in some references, their standard form is written in reversed way. Okay, meaning they start with the constant and then with a sub 1x and then a sub 2x squared, etc. until the last term that they will write is the leading term. Okay, but for our course, for our classes, our standard form will begin with the highest um, degree or with the leading term. Okay, now if a power of the variable is missing, okay, it means that the coefficient of that term is equal to 0. Okay, so there's a possibility that you will not see the power n minus 1. Okay, that means your a sub n minus 1 is actually 0. So 0 times whatever this one is, it's always 0. So it will just disappear. Okay, so if the power of the variable is missing, it means its coefficient is 0. Okay, for example, here we have the polynomial 3x to the 4 plus 2x cubed minus x squared plus x minus 5. So notice the degrees of the variable x is already decreasing. You have 4, 3, 2, 1, and then there's a 0 degree here. Okay, so this is already in standard form. The coefficients, just write the coefficients of the variable. So you have 3, okay, and then 2, and then negative 1, and then positive 1 here, and then negative 5. So 3, 2, negative 1, 1, negative 5. And the highest power of the monomial that you see here is 4. So the degree of the polynomial here is equal to 4. Okay? Next example, we have negative 3x plus 1. So decreasing order or decreasing power for the variable x, it's 1 here and then 0 here. And the coefficients are negative 3 and positive 1. And the highest power that we see here, the power of x here, is equal to 1. So the degree is equal to 1. Okay, next. We have here square root of 3x squared minus x cubed plus 4 plus x. So notice, you have degree 2 and then degree 3 and then degree 0 and then degree 1. So this is not in standard form, but we can rewrite this in standard form. So if we do that, we will have minus x cubed plus square root of 3x squared plus x plus 4. So written this way, we can easily see the ordering for the coefficients. We have negative 1, we have square root of 3, and we have 1 in here, and then the constant 4 in here. And furthermore, we can easily spot the degree of the polynomial. So the highest degree that we see here is equal to 3. Okay, so the degree of the polynomial is equal to 3. Okay, question so far. Next here, look at the way this is written. You have 2x cubed over 3 plus x. But again, remember last time, if we have some fractions, okay, we can always separate the numbers or the constants. So this guy here can be written this way. So 2/3 x cubed and then plus x. So notice we have degree 3 here, and then next to it, it's degree 1. Okay? And therefore, we don't see the degree 2 and the degree 0. So just to emphasize, one of the remarks earlier, that when we don't see the power or we don't see a power of the variable, then the coefficient is equal to 0. So this guy here can actually be written as, so 2/3 x cubed plus 0 x squared plus x plus 0. Okay? And notice this way of writing the polynomial will actually show us the coefficients written properly. So we have 2/3 here and then the 0 here, okay? And then the 1 in here and again another 0 in here, okay? So we inserted those coefficients, the zeros, okay? And the highest power that we see in this polynomial is the exponent equal to 3. So the degree of this polynomial is equal to 3.
Hey,
Okay?
I didn't get it.
Yep.
Why 0x elevates to 2?
Uh-huh.
I
Because, well,
okay.
look at this. You don't see any x squared here, okay, in
Mm-hmm.
this original. So it means, according to the remark that we discussed earlier, if you don't see the variable or if you don't see a power of the variable, it actually means the coefficient is equal to 0. So
Okay.
any number multiplied to 0, it's equals to 0. So you can disregard this term,
Okay.
just like what we did in this part here. The x squared and the constant part, they were disregarded. Okay?
Okay. Thank you.
You're welcome. Okay? And in the future, you don't have to write these guys here. The 0x squared and then the plus 0 here, etc. You don't have to write them. Okay? It's just
Okay.
for an illustration that the coefficients are 2/3, 0, 1, and 0. Okay?
Okay. Thank you.
You're welcome. So I am doing this part because if you are going to pursue um, well, if you are going to take some courses which requires programming of polynomials or etc., um, you will be forced to write the coefficients of the the polynomials. Okay, so if you don't write that zero coefficient, your desired polynomial may not be the same as the one in the output. Okay, so these guys here, we just write them to illustrate the remark earlier. Okay, and possibly for coding purposes in the future. Okay, so let us continue with our next example. Here, the constant 5. So remember, we had the constant 5 earlier. So of course, the coefficient, it's 5. And the degree is equal to 0. Because again, this 5 here, you can actually write this as 5x to the 0. And remember that any non-zero number raised to 0 is equal to 1. So this actually means 5 times 1. And therefore, you just have 5. Okay? And again, for those constants like this, -5 or +1 here or 4 here, you don't have to write this x to the 0. So I'm just writing this here to emphasize that the degree of any constant, okay, the degree of any constant is equal to 0, provided that the constant is not equal to 0 itself. Okay? So to be clear, the degree of any non-zero constant, okay, is equal to 0. Okay? Another example, here you have 2 minus x squared, or this guy here can be written as minus x squared plus 2. So we have power 2, we don't see any power 1, and then we see the constant. So the coefficients are -8, 0, and 2. Okay? So -8, 0, and 2. And again, the 0 appeared because here we have a missing power of x, particularly x raised to 1. Okay? So it means, since it is missing, it means the coefficient is equal to 0. And then the highest degree that we see here, it's exponent equal to 2. So the degree of the polynomial is equal to 2. Okay? And for the last here, let us see what we have. So we have the polynomial 0. Okay? The coefficient is 0. Okay? But I mentioned earlier, if you have the 0 constant or every coefficients that we see are 0 in the polynomial, then we say that the polynomial has no degree. Okay? So let me explain now why the 0 polynomial or the constant 0 as a polynomial has no degree. So first, your 0, okay, this 0 can be written as x or can be written as 0 times x to the 0. Agree? Because x to the 0, we'll just treat it as 1. So 0 times x to the 0, it's still 0. So if this is the case, if we write it this way, the degree here, okay, so let me just write here, degree equals 0, right? If we write this constant here this way. But 0, I can multiply it with x to the 1. And therefore, the degree now, the degree now is equal to 1. And 0 again, I can write it as 0 times x squared, 0 times x cubed, and etc. and you can go on and on and on. Okay? But what will happen to that? What will happen to that? In this case here, we have degree equals 2, and here we have degree equals 3, and we can go on and on and on. So the question is, what is the degree of the constant 0? Should it be 1, or should it be 0, or should it be 1, or 2, etc.? Okay? So mathematicians agreed that in this case, you have the 0 polynomial, then that polynomial, that special polynomial, we will say that it has no degree. So only the 0 polynomial has no degree. Okay?
I have
Question?
question.
Yep.
Yes. Uh, First I understand coefficient, but third zero I don't little bit I'm confused.
Where is the confusing part?
Coefficient zero
The
about
coefficient 0. Here,
third it's yeah a little the
this guy here,
second third
Oh, I think she's saying that it's the fourth.
this guy here, the fourth example.
yeah. Oh, sorry. Yes, fourth.
Yeah, it's the fourth example. So again, let us go back to that part. Okay. So notice, uh, we have written it this way. So you have 2/3 x cubed plus 0x squared, because 0 times whatever x squared is will always be 0. So it will just disappear here, plus x, because x is in here. And then there is no constant here, so plus 0. So that is why if we write all these coefficients, okay, if we write all those coefficients, so this is one coefficient, this is the other coefficient, and then there's a coefficient here, it's actually 1, and then this is the last coefficient. That's why we have 2/3, 0, 1, 0. Okay?
It's not one yet. Zero. It's yeah.
Which one here? This guy here?
Yeah.
No, it's not 0 because it's present there. And remember, any number, any number 1, any number a, if you multiply it by 1, this is equal to a, right?
Yes.
So the multiplier for this x here is actually 1. If you insist that it is 0, then 0x, this is equal to 0, then it must disappear, right?
Mm-hmm.
So if you don't see, if you have the variable, say here x, okay, if you have the variable, okay, and there is no number that you see, there's no number there, it means the number beside it is actually 1, because that number multiplied to 1 is the number.
But where you get it zero?
The 0, it's because it's missing. It's missing here. Look, again, we go back to this. If we look at this part, we only have this, right?
Okay.
But
Mm-hmm.
there is no, where is your x squared? And where is your constant? They disappear,
Okay.
right? They
Yeah.
disappeared. They are not present in this part. It means they are being multiplied to 0 here, just like what we wrote here, right? If they are
Oh.
missing,
Mm-hmm.
they are gone because they were multiplied to 0. That's why they are gone. And therefore, that should be the coefficient. Okay?
Always will be x power 3, x power 2, and x power 1. Okay. Yep.
Okay.
Mm-hmm. Thank you
So
very
it's
much.
clear. You're welcome. So other questions? So we proceed to the last year. So other questions? Okay, so now most of the time in our previous example, we were using letter x or the variable x. We can actually use other variables to represent or other letters to represent variables. So you have here negative 3y squared minus y plus 1 or z cubed minus z squared minus 1. So we can use them, okay? We can use other letters. However, just like in one of the examples earlier, if you are going to combine or if you are going to add or subtract monomials with different letters, meaning with different variables, okay, okay, then you cannot combine them, even if they have the same power, okay? So the variable x represents some quantity. The variable y will represent another quantity, not the same quantity as what x represents. Okay? So just make sure, be consistent. If you are um, using a letter to represent one quantity, then be consistent with that letter only. Because if you use another letter, you cannot combine them. Okay? Now, here are some examples which are not polynomials. This guy here. So 2 over x plus x. Okay? This is not a polynomial because we see if we write 2 over x, we can, if we rewrite 2 over x, we can rewrite it as 2x raised to negative 1. Okay? So remember, if you have negative exponents in the numerator, you can bring it in the denominator and then change the exponent to positive. And if you have exponent, or if you have um, negative exponent from the denominator, you can bring it up to the numerator and change the exponent to positive. So in here, the x here is on the denominator. We bring it up, so we just have 2x raised to negative 1. Okay? But this expression here, 2x raised to negative 1 plus x, it has an expression with an exponent, okay, which is not a non-negative integer. So negative 1 is actually a negative power, okay, or negative integer. So this is not a polynomial. Another expression here, quotient of two polynomials, but the degree of the polynomial in the denominator is greater than 0. Okay, so you have x plus 1 divided by x plus 2. So you have a polynomial in the numerator, you have a polynomial in the denominator, and the degree of the polynomial in the denominator is 1. Okay, so it is greater than 0. Therefore, this is not a polynomial. Okay, to be clear, you can have quotients of two polynomials, but the ending is still a polynomial. So how do we do that? Here, say x plus 1 divided by 2. So this is a polynomial here. Constant is a polynomial. So polynomial, poly, with degree equal to 1. Here also poly with degree equal to 0. So this guy here, this is still a polynomial because you can write this as 1 half x plus 1 half. Okay? So 1 half x plus 1 half. So this is still a polynomial. So if the polynomial in the denominator has degree 0, meaning it's just a constant, then you can still have a polynomial in the end. Otherwise, it's no longer a polynomial, just like in the example here. Numerator, degree 1, denominator, degree 1. this is no longer a polynomial. Okay? Question. Now, one of the goals for this course is to do some operations in polynomial. Sorry, one of the goals for this lecture is to work on or do some operations on polynomial. Okay? So first one, we can add or subtract polynomials. And if we do that, or when we do that, we are actually combining like terms. So you can have a polynomial. So you look at each of the monomials, and then another polynomial, you will add it from the first polynomial. You have to look at the monomials in the second polynomial and find its corresponding like term to the other polynomial and then combine them. Okay? So what I'm saying is the following. So let us try to illustrate that. Okay? So here are the examples we're gonna work on off the record. So try to write them or try to hit pause, and then I will now pause the recording uh, so that we can work on these two examples. So now we're back. This time we want to multiply polynomials. So polynomials can be multiplied with each other using the distributive property. So we just distribute one term or one polynomial into each of the terms in the other polynomial, etc. Okay? So here are again the examples that we will be working on off the record. So I'll hit pause again. Another method of multiplying polynomials is with the use of FOIL. But in this case, we just have to multiply two binomials, meaning two terms. So they will be of the form ax plus b and then cx plus d. Okay? So FOIL method, FOIL. So first, outer, inner, last. So what does this mean? We multiply. So first, what do this first, outer, inner, last um, represent? First, meaning you have the first terms. So in this product here, you have AX and then the CX. Those are the first term. And then the outer, it means in the outer brackets here. So AX in the first term or in the first factor, and then D on the second factor. So they are in the outside. Okay, when you write the multiplication this way or the product this way. And then the inner, those are the one inside. Okay, so if we consider this as outer, then the ones inside are the other terms in the um, product. And then the last, they are the last terms for each of your factor. So in this factor, you have B, and then on this factor, you have D. Okay? So first, and then outer, and then inner, and then last. So you just do the multiplication that way. So you have the first here, AX times CX. Outer, you have AX times D. Inner, you have B times CX. Then the last, B times D. And then you do the multiplication and then you just simplify. Okay? Of course, it will be easier to see if we consider using this method via or in the examples. So we will work on these examples for this method. So again, I'm hitting pause, um, and we will do the solutions to this example off the record. So now let us consider special products. So the last two examples that we just did, um, you can simplify them using, or you can simplify the solution using these special products. Okay, so squares of binomials, or what we call the perfect squares. Okay, so it's like there is a formula in here. In fact, this is a formula. So you have x plus a squared. Okay, so x plus a, then there's bracket, and then you raise it to power 2. Okay, and this one can be expanded into x squared plus 2ax plus a squared. So square of the first term plus twice the product of the terms. So 2 times a times x plus square of the second term. Square of the second term. If it were negative, instead of plus you have minus, the middle part is also minus. Okay? So here are the examples that we are going to work on off the record. So another special product, this is difference of two squares. Okay, so you have x plus a, x minus a. So if you multiplied x plus a times x minus a, this is simply x squared minus a squared. So one is plus, the other is minus. You multiply them. Okay, all you have to do is you get the square of the first term, so x squared, and then minus square of the second term, so a squared. Okay, and here are the examples we're gonna work on. So for this special product, you have cubes of binomial or perfect cubes. Um, we I usually include this in the discussion because there is a very good formula in here. Okay, but I will not further discuss how we're gonna look at this. Oh, anyway, let us see where we'll be heading to. Okay, so in here you have the formula x plus a cubed equals x cubed plus 3a x squared plus 3a squared x plus a cubed. And then if there is a minus, you have x minus a cubed equals x cubed minus 3ax squared plus 3a squared x minus a cubed. So definitely you won't be able to memorize this. Yeah? So I will, if I'm going to ask you to do this, to do some examples or some problems involving cubing binomials using this formula, I will have to include the formula in the problem. Okay, so you won't have to think about how you're going to do this. Okay, but let us see. Let us see here. So these are the examples. So x plus 3 cube, or x plus 3 quantity cube, and then x minus 5 quantity cube. So for these two examples, I will do this while recording. Okay, so you can go back to this later if you need to. Okay, so in here you have x plus 3 cube. So according to this formula, this is your first, and then your a here, it's your 3. So according to this formula, you will have x cubed. Okay, so we are just copying this. plus there's a 3 here, okay? So plus 3, and then the a here, it's 3 here also. So times 3, and then the x squared, so x squared in here, plus there's a 3 here again, so you have 3, and then a squared, okay, a squared. So this one here, it's 3 squared, and then the x, okay, and then finally plus a cube, so 3 cube. Then if we simplify this is just x cubed plus 3 times 3, that's just 9, so 9x squared. Then here, 3 times 3 squared here, it's 9, and then times 3. So you have 27x, and then the 3 cube, 3 times 3 times 3, that will also give you 27. So straight from the formula. Straight from the formula. This will be the final answer to that.
Sir, I have a question.
Yes?
Yes, so besides the formula, is there like a simpler way to do it? Like
I will try to show you a simpler way to do that. But actually, that's the formula. So that's one way to derive this formula. But I will show you that.
We don't need to simplify.
This
Or-
cannot be
Yeah.
simplified anymore.
Okay, because then we have 27/9, and then divide by 3.
But this guy here doesn't have a 3,
Oh yeah.
right?
Okay,
You
okay,
cannot simplify that.
okay,
Even if there's a 3 there, you cannot just remove the 3. So you just write it as is. This is not an equation. This is not equal to 0. Okay?
okay,
So we will go there later in the course. But whatever you see as a final expression, just write it that way and do not remove common factors or whatsoever. So we will go to that part. Okay?
okay. Thank you.
You're welcome. For this example, you have x minus 5 cubed. So this time we have a minus here. So we'll follow this formula. Okay? So for this, we will have x cubed. Okay? This is the x cubed, x. And then there's a minus here. So minus 3 times a. This time our a is 5. And then x squared from here. Then here we have now plus. So plus 3. And then the a squared. So you have 5 squared. And then x. And then minus in here. Minus 5 cubed. Okay? And then just simplify. You will have x cubed minus. Here you have 3 times 5. So what is this? This is 15 x squared. And then here you have 3 times 5 squared. 5 squared, that's 25. And then 25 times 3, that's 75. So 75x. And then here you have minus 5 cubed. 5 cubed, it's 5 times 5, that's 25. Times 5 again, that's 125. So this is the final answer to this problem. Okay? Okay. So just like I promised, is there other way to determine this? Okay? To determine this formula. So let me go back to this part so I will have a lot of space for this guy here. Okay? So this guy here, binomials, cubes of binomials, they can easily be derived using uh, the binomial expansion. If you have heard that, if you have taken statistics course, you might have heard binomial expansion. Okay, but what I'm going to illustrate to you here is the Pascal's triangle. So what is a Pascal's triangle? A Pascal's triangle is something like this. So you construct the Pascal's triangle. You start with 1, and then you go down left and then right. And then you add. So there's no other number to add in here. So you'll just have 1 in here and then 1 in here. Okay? Now, for this, you also put it down here and then down here. Okay? So binomial. So one leg here, one leg here. Okay? This one also binomial, one leg here and one leg here. Okay? So you have, let me write this. So there's a leg here and then there's a leg here. And then there will be a leg here, leg here. This one will also have a leg and another leg here. Okay? So if there are two legs in one point, just like this, you will have to add the numbers above it. So in here, there's one leg here. You'll just have 1. Okay? Here, there's one leg in here from 1, and then one leg in here from 1. You have to add them. You will get 2. In here, there's only one leg here. That's just 1. You continue, binomial. So one leg here, one leg here. For this leg here, leg here, leg here, and then leg here. Again, this is just one leg. So you'll just get 1. Here you have leg for 1. There's another leg for 2. So 1 plus 2, that becomes 3. Here, leg for 2, leg for 1, 2 plus 1, that's 3. Okay? And then here, just leg for 1, this is 1. So I'll stop on this triangle. You can continue this triangle. Okay? So what does this mean? What does these numbers here represent? So in the first, in this guy here, okay, so let me write this guy here. Okay, so on the first line, this is actually x plus a to the 0. So x plus a to the 0. So any number raised to 0, as long as it's non-zero, as long as this number is non-zero, it's always 1. This guy here, it's x plus a to the 1. Okay? This guy here, it's x plus a squared. And this guy here, it's x plus a cubed. Okay? What do these numbers represent? They represent the coefficient of x and a. To the 0, it's just the constant 1. To the 1, you just copy x and a. To the 2, you have 1 to 1. Okay? So there is a 1, there should be a 1 here, there should be a 2 here, and there should be a 1 here. But now, what are the terms? You look at the first term, okay? You look at the first term, and then you start with the highest possible power, which is squared. So you have x squared. And then you write it. You write it in decreasing power. So x squared, and then your x here, and then your x to the 0 here. Okay? So x squared, and then you have your x, and then so x to the 1 here, and then x to the 0 here. You look at A, you start with the lowest power, and then write it in increasing power. So that means you have A to the 0 here, A to the 1 here, and then A to the 2 here. And then if it's plus, you write everything plus in the middle. Plus here, plus here. So what will you get? You will get x squared plus 2ax plus a squared. That's the formula. Got it? Let us look at that x plus 3, x plus a cubed. So x plus a cubed. So this 1, 3, 3, 1, they represent the coefficients. So you have 1, and then 3, and then 3, and then 1. And then you look at the first term. Here, x, you write decreasing powers for x, starting with the highest possible power, which is 3. So in here, you have x cubed, x squared, x, x to the 0. So decreasing power, 3, 2, 1, and then 0. Then the second term here, a. The second term here, a. You write it in increasing power, starting from 0, just like what we did in here. So in here, you will have a to the 0, a to the 1, a to the 2, and a to the 3. And then if it is plus, you write plus. You write plus. So plus here, and then plus here. And then just rewrite this, just simplify or rewrite this in a more beautiful manner. So you just have 1 times x cubed times a to the 0. So that's just your x cubed plus. You have 3a to the 1 x squared. So 3ax squared plus 3a squared x here. And then you have 1 times a cubed times x to the 0. So this is just plus a cubed. And this is your formula in here. Okay? So you can use this Pascal's triangle. Okay? What if it were minus, just like this? This one is minus. If it were minus, you write alternating sign. Plus, minus, plus, minus. Even if it were in squared, if instead you have x minus a, so you will have plus, minus, plus. And you go back to your formula, it's the same formula. So alternating. Okay? You can do the same thing in the fourth power, x plus a to the 4. So you go down the binomial here, or the binary here, or the Pascal's triangle here. You can go down there. So you will have 1, and then 1 plus 3, that's 4. 3 plus 3, that's 6 in here. 3 plus 1, that's 4 again, and then the 1 there. Okay? You can go and use that. Use the same method that we did in here. First, addend, or for first in the factor here, decreasing power starting with the highest possible power. So if you were in the to the fourth power, x to the fourth, that's the first, then x cubed, x squared, x, and then x to the 0. And then for the second addend in the term, or second addend in the factor, you write it increasing power. So a to the 0, a to the 1, a to the 2, a to the 3, a to the 4. And you will have a formula for your x plus a to the 4th power. Okay? So that's one way to memorize this formula. Okay? And you can do that for higher powers. So question.
No.
Okay. So now we had addition and subtraction. We also had multiplication. This time we'll do division. But for division of polynomials, we will only have polynomial divided by a monomial. Okay? So single term in the denominator or in the divisor. Okay? So we will not consider polynomial divided by polynomial where the denominator or the divisor have different powers of the variable. Okay? So just by a monomial for our course. So this is what we always have since studying division in our primary schools. So dividend divided by divisor. This can be written as quotient plus the remainder divided by the divisor. Okay? So this is always the case. So when dividing a polynomial by a monomial, what we're going to do is to divide each term of the polynomial by the monomial. So meaning, if we have a polynomial, okay, with two or more terms, we are going to separate them. And then the divisor will just be distributed to each of these terms in the dividend. So to illustrate that further, let us consider working on this example, but we will do the solution of the record. So polynomials in two variables. So a monomial in two variables, x and y, it has the form a x to the n, y to the m, where a is constant, x and y are variables. Okay, and n and m are non-negative integers. Okay, the degree of a monomial is the sum of the powers of the variable. So in this case, you have n plus m. Okay, you have two variables. Degree of x is n, degree of y is m, or power of x is n, power of y is m. The degree of the term a x to the n, y to the m, it's n plus m. Okay? Now, these are examples. You have 3xy cubed. You have minus x squared y squared. You also have 2x cubed y. These are all monomials. They are just like this. But notice, x has power 1 is power 1, y has power 3, 1 plus 3 equals 4. So the degree of the monomial here is equal to 4. Here, x has power 2, y has power 2, 2 plus 2, degree 4. Okay? Here, you have x power 3, y has power 1. So 3 plus 1, that's still 4. So all of these polynomials, they are all have degree 4. Okay? So a polynomial in two variables is a sum of monomials in two variables. So you can add all of them, you can get a polynomial, just like polynomials in one variable. The degree of the polynomial in two variables is the highest degree of all the monomials with non-zero coefficients. Okay? So you will look at the degree of each monomial, you will choose the highest power. So for example, in here, x cubed minus 2xy plus 5x squared y squared minus y plus 1. Degree of this monomial, it's 3. So x to the power 3. For this monomial, x has power 1, y has power 1, 1 plus 1. The degree here, it's 2. In here, x has power 2, y has power 2, 2 plus 2, 4. So the degree of this monomial, it's 4. Here you have y has power 1, so degree of this monomial is 1. This is constant, so the degree of the monomial is 0. So the highest power that we see, it's equal to 4, coming from this. Okay, coming from this. Okay. Now, the last part of this discussion, so we'll just finish this in 4 minutes. The last part is substitution and evaluation. So substitution or evaluation, it's the replacement of the variable, replacement or substitution of the variable. So this should be or, okay, takes place each time the variable appear in the expression.
I have a question.
Yes,
The page before, what we do, we just remember and that's it.
yes, that's it.
We
Although
don't.
this might appear sometime in the future, but at least you know this is how we define it. And this is still polynomial. Right now, don't think about that.
Okay.
Uh-huh.
Thank you.
You're welcome. So replacement or substitution of the variables takes place each time the variable appear in the expression. So for example, 3x squared minus 5x plus 26 for x equals negative 1. Okay, so this means we want to replace x with negative 1. So in here, you will have 3 times negative 1 squared minus 5 times negative 1, then plus 26. Okay, so this one equals 3, and the negative 1 squared, negative 1 times negative 1, that's positive 1. So 3 times 1, that's 3. And then here, minus 5 times negative 1. So negative 5 times negative 1, this becomes positive 5. So you will have plus 5. And then you have 26 here, so plus 26. And therefore, this is equal to 34. Correct? So that's replacement. So we change x with some number. The actual number actually is negative 1. And another problem here. So 9x minus 5y plus 2xy. So this is a polynomial in two variables. But we want to replace x with 2 and y with 1. So in here, we will have 9 times 2, okay, minus 5y, so y is 1, and then plus 2 times x is 2, and then y is equal to 1. Good? Then we'll just have to simplify this. 9 times 2, that's 18, minus 5 times 1, that's 5, and then plus 2 times 2 times 1, this is just 4. So this is equal to 17. So this is the value for this substitution. Okay? So
Okay.
question so far. So it's already 8:30, just 1 minute, okay, to show you this. So work on as many problems as you can on page 13 and page 14 of 016 module. Okay?